Hello, my name is Ryan Keeble. I'm a technical artist at Mighty Games, and I'll be talking to you today about post-processing and rendering in VR with Unity's URP. Today we'll be talking about what SHOOTY SKIES OVERDRIVE is and what we wanted to achieve with our post-processing, what Unity's URP render features and passes are, and what Unity's URP scriptable render is, a little bit about the Oculus Quest 2 hardware and how that has implications for all the work that we're trying to do. Some of the optimizations that we've been able to put into SHOOTY SKIES OVERDRIVE to be able to achieve the post-processing effects that we wanted, how we applied color grading, the post-processing challenges we experienced on the Quest 2, and HDR aliasing issues and solutions that we encountered when doing this work. First of all, I'm not a graphics programmer. But we're going to cover a lot of graphics programming concepts. I've had to learn them pretty hard over the course of doing this project, so hopefully I can explain them all to you fairly well. So SHOOTY SKIES OVERDRIVE is a frenetic arcade shoot 'em up full of colourful, retro and inane characters. It shipped last year. It is the VR successor to SHOOTY SKIES, our mobile title, and it is a room scale bullet hell experience. In August, we released a graphics update to it that had a mode where you could turn on post-processing, including bloom, and that ran at 72 frames per second. We built it from the ground up using Unity's URP framework, which when we looked at which framework to use with Unity, we really liked the look of the URP as it came with optimized shaders and settings that were VR ready. Its scriptable render features allowed for additional functionality that we use throughout production in bits and pieces. We found it very easy to scale the quality across platforms because when we launched, we predominantly targeted the Quest 1, but we also launched on PC VR. And our PC VR product shipped with post-processing, which was basically bloom, vignette, and some color grading. And those effects are what we wanted to bring in our graphics update in August. So bloom is a fantastic effect that helps to really improve the overall visual quality of a game with emissive lighting. It allows bright objects to bleed over their surroundings and kind of mimics camera lens effects, but also gives that natural glow of neon lights and light emission when in contact with surfaces. It provides far more context and visual feedback to an experience, I find, and it is great for retro neon art direction, which we had when we were building levels that were based around synthwave 1980s art and that sort of neon style. The second thing that we wanted to bring across into our graphics update for the Quest 2 was color grading, which is a very important mastering tool. It provides a lot more flexibility in controlling your output color at the end of all the steps of doing lighting, texturing, and all that. You can really sort of master it at the end with post-processing color grading, and really unifying the overall palette of a scene and help define the mood and tone to get the look and feel and experience of the game just how you want it. We used a lot of light baking in our development, so we found it a lot faster to tweak our color grading than to rebake our lighting to get the style and feel of the game just right. So in order to introduce those aspects onto the Quest 2, we really had to start looking at scriptable rendering and how to bring that on board. So scriptable render features are a great tool with Unity's URP for creating rendering effects. It's essentially a scriptable interface for render passes, and it plugs right into Unity's rendering engine. And it's very high level and fairly easy to work with. So by high level, I mean you're dealing with the Unity scripting language and you don't have to worry about writing any of your own low level graphics APIs. So you don't need to know Vulkan commands to be able to set up a rendering pass and execute it. You can just easily work within Unity's high level scripting languages. And it is really great for visual effects and post-processing effects. So I'm going to be focusing quite predominantly on custom post effects with these scriptable render features and scriptable render passes, but predominantly it's another example that you'll see quite often in tutorials is outlines. and also you can use it for building screen space reflections, ambient occlusion, planar reflections into your games. And there's a lot of great resources out for these now. So I've left a few links in a page at the end of the slide. So one effect that I was mucking around with earlier this year, just as a bit of side fun, was a color blend post-processing effect passed. And what this is effectively doing is combining a custom balloon, a vignette, and tint and screen tint effects into one scriptable render pass. And this is all set up through a scriptable render feature. Each application of bloom, vignette, or tint can be blended with a color blending operation in this effect. And that's basically similar to how layer blending works in Photoshop. So if you want to blend a layer with a screen pass with another layer, we can do that with post-processing here, or linear dodge, or multiply, or darken, or any of those sort of standard Photoshop layer and blending effects. And there's a link to this repo in the summary as well. So how this works is, in the render feature, we start to initialize our data. So we set up our descriptors for our render buffer, determining the format, the width, the resolution, and things like that, how many depth buffers, depth bits we're going to use. And then we also sort out all our operational parameters. So what blend types we're going to use in this example. Are we going to be using color dodge? Are we going to be using screen? Are we going to be using lighten? All those sort of things, they have to be passed to the shader so they know what operations to perform, as well as the strength of those blends. We also need to organize what our bloom parameters are and our vignette parameters are. So those are all organized when we start to initialize data in our settings of the render feature. So then what we do is we'll set up our buffers, and we're creating our render textures here by using those descriptors, and we're sending those parameters to the shader. And once we have all those buffers set, we then go through and queue all commands. So we instruct the command buffer on what actions to perform on what render buffers. And in this case, we're copying the camera's color, and then with that copied camera color buffer, we are then performing a bloom pyramid on it, and then we're also doing another blit where we do vignette, tint, and combine the bloom all together. And all those three things are blit commands. So they're sending a source image, a source handle, and a destination handle to the command buffer to say, hey, take the source and all the thing, take this source, do all this stuff to it, and then pass it out to this destination buffer. And then that all gets executed at the end of the pipeline once it's passed out from the render feature into Unity's under the hood system, the scriptable renderer. And what happens here is all the shader options that we've queued up for all our blit commands are then executed, and we write that out to, and that at the very end, that all gets written back out to the camera color so that we can see it on whatever display. And after that, we just do a quick cleanup where we release all our render textures and we clear the command buffer so we can move on to our next frame. I find that most of the time a render feature will suffice for the bulk of the work you're doing, but they do have shortcomings, and these shortcomings were critical in doing our work for our graphics update. And mainly, the biggest shortcoming is that it has a kind of closed circuit approach in the way it handles a render pass, and it's very difficult to move render buffers between features. So everything that happens within a scriptable render feature and a scriptable render pass sort of is executed in there, and you can't really get to it once it's already done. So everything's set off to the command buffer, is processed, and it's completed, it's cleaned up, and bang, you're done and dusted. You can't really do anything more with it after it, and you certainly can't really do too much before that. And we found that render buffer memory must be stored between features. So as soon as something is processed, it needs to be written back so that the display can read it again later. And this had some optimization implications later. As we saw in the previous example, in order to do a full screen effect, you're also requiring a copy pass where we're going to be copying what the current camera color texture is so we can work on it. And this also has performance implications, as we'll see later. And finally, we couldn't really control what the camera initialization is, so we can't set up what the camera description is going to be before we start rendering altogether, and we don't really have any control over the final output execution, so how we write all our effects and color data and color data to the final display. And what Unity will do when you start working with render features is force a final blit. So that'll take everything that you've processed and basically do another copy function where it copies whatever the camera color is ready for transfer to the final display destination. And that also has performance implications. So what we can do is start to look at using the scriptable renderer, which is a core feature of Unity's URP and HDRP, but we'll be focusing predominantly on the URP today. It is essentially the next layer down in the render pipeline. Unity's URP forward renderer that comes with the URP, and if you attach a render pipeline asset in the graphic settings, you're essentially attaching Unity's standard scriptable renderer. And what that's doing is handling all the rendering data initialization and all your render pass queuing. So it essentially forms a framework for bolting on additional render passes or extending additional ones. And as you can see in this diagram example, we're taking all these render passes that we're queuing up, so opaques, transparents, post-processing, whatever, and they're all getting queued in through the scriptable renderer and then set through, deep under the hood to the low-level operations and then out to your display. And what we can do is we can write our own. Instead of using Unity's forward renderer, we can write our own, and this has a fair more benefits than just using a scriptable render feature and a single scriptable render pass. So Unity's URP forward renderer is really set up to handle numerous toggles and states. I mean, you can do so much stuff with Unity on the editor end that the forward renderer under the hood really has to handle all those different states to push out what the final rendering output's going to be. But when we start working with a custom renderer, we can actually start to be far more explicit with our design and our architecture, and this gives us a lot more freedom to be flexible in how we customize and optimize our render passes and effects. And we can really start to specify how we want our rendering data to be set up, as well as have a bit more direct management over our render buffer memory and how we do those operations. And for the biggest boon is being able to control what that final output is going to be and how it's going to be executed. It's also great for creating additional G buffers and writing to them, and essentially you can write your own deferred renderer using a custom scriptable renderer, but we'll leave that for another day. It's important to note though when you are dealing with render effects with Unity that debugging rendering issues is very different from debugging code, and you can't really stack trace issues the same way as you can in standard code. So things like the frame debugger and render doc are your friends, and you really need a keen eye to be able to spot the difference and understand the issues. One bug that I encountered when I was writing the color blending render pass effect was that I'd forgotten to clear out one of my bloom buffers in the cleanup pass, and that was causing a couple of the buffers to be rendered at half resolution, and I couldn't work out why. It was only the frame debugger that could show me that that these things were being rendered at half resolution, and then I had to scrape through the code to find out where that issue was. So now let's have a quick talk about VR hardware and what we're targeting and what the implications of that is. So the Oculus Quest 2 uses a Snapdragon XR2 tiled renderer GPU. And what that is designed to do is minimize the amount of external memory access when we're doing fragment shading. So the way it works is it grabs all the attributes that you need and sends that up to the tiled memory. Sorry, I'll start again. It basically breaks down the screen into all buckets of tiles, all these different buckets and tiles to render asynchronously, and for each bucket or tile it grabs all the attributes it needs. So initially it'll grab all your vertex attributes, pass that up, then work out what geometry is going to be displayed where, and then it'll start the fragment pass. And it's really good at moving between the fragment shader and its local tile. When it's doing its fragment shading, it's really good at moving in and out of its own local tile memory. So everything that gets passed up there, so textures, vertices, anything else external that the fragment shader needs to know about in order to compute its output gets sent up to the local tile memory, and it's really fast at moving in and out of that. And then once it starts to go back out again and gets written to the frame buffer, it is now a really slow transfer process. So we want to be able to make sure that as many things get passed up to the tile memory as possible, work within that as much as possible before sending things back out again. So when you start to work with additional render passes, you start to add additional costs for even just reading and writing those render buffers to external memory. And in my experience, it can take anywhere between 1 to 2 milliseconds, which really adds up when you're trying to render at 72 frames per second. Finally, the Oculus Quest 2 frame buffers are optimized for 32-bit buffers, not 64-bit HDR buffers. And so the extra precision and extra data that's contained in a 64-bit HDR buffer takes a fair bit more processing and transfer time as well. And that's something to be aware of when you want to add things like bloom in post-processing, because they generally require 64-bit HDR buffers. So as we can see from that, render features can have a significant cost on the Oculus GPU. Even a basic saturation render path like what we've done with this image can incur the following costs. So the saturation path itself, where we reload back up to tile memory and then perform an operation where we take the color and convert it to a grayscale, then we write it back out again, takes 2 milliseconds. And then because we're using a render feature to do this, Unity then decides that, hey, we're going to do another final blit where we copy it again and send that off to the display, where it's not really actually performing anything in that final blit other than another copy pass. So we need a lot more bandwidth to be able to do what we want to do. And so that requires your game to be pretty heavily optimized in order to be able to pull off these effects. So we did a lot of work optimizing Shooty prior to this update when we released the game. And I gave a good talk about this last year at the Technical Games Conference, and that media is still up there on the internet, and I've provided a link in the summary. So if you want more detail on what we're about to talk about, you can go have a look there. So one big thing that we optimized heavily was our draw calls. So Oculus recommends about 200 to 300 draw calls for a single player first person experience. And as a bullet hell experience, we require a lot of objects and a lot of draw calls to be happening in any one single frame. So we want to make sure that we're sharing materials, textures and shaders to maximize dynamic batching as much as we can. Do static batching for our environment so that the meshes get combined and they can also be rendered in a single draw call. Then we also did something clever with our enemies, because all our enemies are animating using model swapping techniques. We split our enemies up into a shareable base model with separate animating parts. So if we take a look at this example, we have 3 variations of a YouTube enemy where the base monitor remains the same, but each enemy has one type of screen it displays and flicks between 2 frames. So by splitting it up, rather than outputting each model 3 times with a base and the monitors combined for each frame swap, we exported it out so that the base remained constant, but the frames were swapping and just positioned within that base. And that allowed us to make sure that the base was always being batched, because we couldn't guarantee that the monitor frames would allow for synchronous batching across frames as our flickering between the screens. So yeah, in that instance, we can make sure, yeah, I'll move on. Another thing was that we didn't have any albedo textures, normal maps or shadow maps in our game. Just given the nature of the game, we didn't need to have any sort of shadows in there because we weren't really ever looking at the ground. Everything was up in the air. So shadows didn't really have too much of an impact on how the user experienced the game. It didn't feel uncanny without them. We used vertex colors baked into our model data in our modeling program, and we use vertex lights throughout the game for any sort of dynamic lighting. We also bake lighting into static objects and dynamic objects. So for our dynamic objects, we baked and shared occlusion textures to give them a bit more depth and fidelity. And we also used baked cube maps for sampling for reflective lighting on our dynamic assets. And we light mapped our background environments so that we can get as much value out of our lighting there, as well as far more fidelity in our lighting and shadows in our baked environment. So in this example on the right, we've got 3 AO textures atlas together for 3 different enemy models. That's then added with a cube map reflection pass, and we get this nice looking ambient color pass down there in the bottom left, and then we add our vertex colors and our vertex lighting back on top of that for our final finished asset. And it's got some nice sort of almost Fresnel effects with how the colors being reflected as well as some nice little bit of depth with the occlusion in between the edges of the model. Another thing we worked on doing was making sure that our draw order was optimized correctly. And by this, we could basically take a look at our game as, because it was an arena style game, we had arena style gameplay, it provided a fixed area for the player to be in. So we always knew that the player was going to be rendered from a certain position. Well, you don't see the player, but we always knew that the camera was going to render out from the player's position. It's going to be fixed within the world. And enemies would then be spawned relative to the player's position. So as a player, I'm standing in the middle of an environment that's surrounding me, and between me and the environment, our character is being rendered in our hand. The bullets are being rendered, the enemies are being rendered beyond that, and the bullets are passing between the enemies and me as they're trying to shoot me. And behind all of that is our environment. So we could then be very deterministic in our opaque object queue order. And so we can see here we can render our pilot first, and then we're going to render our bullets first because they're going to be between us and our enemies. Then we can render our enemies behind the bullets, and then finally we can render our background. And what this means is that we're going to have less overdraw per fragment, because everything that's going to be rendered behind our player is going to get discarded because we already have the exact rendering data that we need there, and so on so forth for each single layer. And that's just done through managing material queue orders, so setting the player to 0, whereas the environment to 2000 in Unity's object ordering system. So with all those optimizations, we have a really good base for our frame rate. Our opaques are being rendered in 11 milliseconds, our skybox is being rendered in 1.2 milliseconds, and our transparents are being rendered in about 1.9 milliseconds for this particular image here. So that's great. That gives us quite a bit of headroom to start adding some additional effects on top. And our total frame time with all that is 18.5 milliseconds with everything else that Unity's doing under hood to get the display out. So the first thing I want to talk about with effects is color grading, because we ultimately didn't actually end up using any render features or passes to do color grading. We found that color grading was far simpler to add than bloom. We ultimately only needed to grade our environments to adjust the baked lighting output. As anybody who's ever worked with baked lighting output before, it can be very difficult and very fiddly to get right every single time, and it is a long process to iterate on. And we wanted a different grade per scene so that each world felt a bit more, had its own tone and feel rather than having a global grade that went with it. So we wanted to make sure that that specific toning was not going to have an effect on our characters or our world UI, which were a bit more constant, and we were very happy with how our characters were appearing, but we didn't want our world UI to be affected by the color grading at all. So to that end, we basically just went with a per object LUT transformation. So we added a LUT transformation into the fragment pass of our environment assets, and we generated a 2D LUT, 2D LUTs in Photoshop by taking a screenshot of our environment and performing blending effects on that. So in this example, we had a bit of vibrance levels and gradient map image adjustments, and then that was then saved out over our LUT image there in the bottom right of the screenshot. And that was passed as a global texture from our environment lighting objects to the environment shaders. And this was actually cheap enough that we were able to add the support to the Quest 1 in our graphics update as well. So that was a huge win. And we were really happy with the results there. So we can, in this example, we've got some really nice tone coming back in once we've got the color grading on, and it feels like it's got a bit more life and depth to it. So we were really happy with that outcome. Bloom was tricky, and I think there's been a lot of people out there developing on VR who've wanted to implement Bloom and hit some major roadblocks. So hopefully we can provide some valuable advice to hopefully get you to be able to implement it in your game. Bloom is basically a blend of several downscaled and filtered HDR bluffers blurred with a Gaussian kernel. So we take our camera color and we discard any pixels that aren't HDR, and then we continually downscale that and blur it. So we downscale it, blur horizontally, downscale it again, blur vertically, and do that over and over again for a certain amount of steps. And then we take all those different blur passes that we've made and start to slowly combine, not slowly, well, hopefully not slowly, but combine them back together till we have a final nice blend, and then we send that off to be added to our color in our final render pass. So we have all these buffers that, then get blended together and added to the camera color. What we have with that then is multiple active render buffers with inherent read-write costs, and that can be an issue on our tiled renderer, as we looked at before. And ultimately what we're doing that's really expensive is fetching additional pixels across multiple tiles. So when we want to find out the pixel of a particular, the color of a particular pixel to be able to blur it, we need to find the average of the colors, the other pixels around it. We actually need to find all the colors of all the colors of the pixel around it on a horizontal or vertical alignment. So we're sampling not just our pixel, but the pixel next to it, the pixel next to it, the pixel next to it, and the pixel next to it. And if any of those pixels happen to be on another tile, then we have to now read another tile again from external memory to be able to access that single pixel and read that out, and then determine what our weighted blur should be. So that can be a bit tricky to manage. I found that this YouTube channel, Computer File, and this guy in particular talking about blur filters was really helpful in understanding exactly how blur is working under the hood. So I've added a link to that in the summary as well. We found that Unity's bloom was actually fairly well optimized, but we tried to optimize it a bit further to be able to get some more gains there. We essentially optimized the precision and trimmed out any unused code. We reduced the number of steps, so the amount of times we're downscaling, then upscaling again from about 12 to 8. And we tried to reduce the amount of blur taps, so the amount of times we're sampling adjacent pixels. And we tried doing a thing where we masked the camera color before thresholding. So prior to determining what, prior to Unity doing its thresholding filter pass, where it sort of does some calculations on the pixel to determine whether or not it should be sent to the next buffer, we basically just went in and hard found whether or not the pixel had a certain value to it in its R or G or B channel. So then we could know that it was a HDR color. And anything else after that, we just went and rejected it. But it didn't really save us any render time, but I just wanted to mention it because it's going to be useful later. So in order to take that bloom and put that in, that optimized bloom and put that in the game, we started looking at using our own scriptable render pass. So we would have our render pass for opaques, our skybox, and our transparents, and then we had our own render pass for post-processing that we added on at the end, removing Unity's post-processing. We basically rewrote Unity's post-processing pass, cleaned it out, and added only what we needed in a very explicit manner, and then we were able to do our bloom filter in there, our bloom down and up, map render passing there, and then we were able to have our own final bit operation within that render part, the post-processing render pass, where we added our bloom and did our output to our display. So we're kind of smushing our bloom post-processing pass that we would normally do in a render feature with the final bit, so they were executed in a single render pass operation. And this was a lot faster. But it introduced some additional, adding bloom introduced some additional issues that I hadn't thought of prior, and it turned out it took a lot more work to polish out, and that was aliasing. So aliasing is a significant issue on VR platforms in general. It's something that a lot of people smarter than me have been spending years trying to work out how to solve best. And what the current standard is to use multi-sampled anti-aliasing, which will solve about 90% of aliasing issues fairly cheaply and pretty effectively. But hardware anti-aliasing, such as multi-sampled anti-aliasing, is not compatible with HDR rendering. And that's because the amount of color bandwidth you're using just can't be solved on the hardware level. So what you can see in this example here on the right is you have a really nice smooth line down until we start to get start to get combined with the intense light source in the background, and then we can start to see the step staircasing that's occurring in this image example. So that's where the multi-sample blending is failing when we start to use HDR color buffers. And in our game, we had some significant issues. So now we were using emissive colors or HDR buffers for our window lights and our monitors, some enemy screens, and they were starting to cause aliasing issues. And you can see it here as step staircases, but in an actual VR application where you can tilt your head in any variety of manner, it's really exasperated and really ruins the experience. So it was imperative that we basically found a way to smooth that out before we could release the update. So there was a couple of additional solutions that we started to explore prior to our final solution. One of them was just to say, hey, why do we need a high dynamic range bloom? Why can't we do it with standard dynamic range? But then you're just thresholding sort of like the last 95% of your captured color range, and this would blow out our whites in our world and also our world space UI. It also gave us less control over our per object intensities, and our art was not designed with this approach in mind. So it was sort of like had way too much impact, and we didn't want it. Another way was to look at using a glow buffer, where we would in another pass write all our objects that we wanted to glow to a glow buffer, and then in post-processing pass we could take that glow buffer and do our blur operations to it. But each time we are rendering another object to our glow buffer, it's making another draw call happen. And given the amount of draw calls we were using already for our bullet hell experience, we started to really approach our draw call limit, and was far too expensive just in that approach. So we had to scrap that. But we found here that the SRP was probably more useful than anything else in finding our final solutions, because we needed to trial a lot of different filters and optimizations to get the required result. And working within our own scriptable renderer, we had far more control over each stage in the rendering process, and we could configure things differently. More options were exposed that we could work with, and we had one easy location to work with. And so that was really helpful for testing and iterating this process as we tried to come to a solution. Another solution that we looked at was tone map resolve, which is often used in modern games now, and that's to basically, rather than have the multi-sampling anti-aliasing resolved when you're rendering your objects, we bind the multi-sample samples to the camera attachments to resolve later in our own fashion. So then we can perform a tone map and inverse tone map operations in a resolve class prior to performing our bloom. So we'd load up each multi-sample, would tone map it, and then would weight it and add it back to whatever final color output when we had. Our final color output, and when we'd done that for the amount of samples that we would have, we could then take that result and inverse tone map it to get our colors back. And in order to do this, we needed to be able to customize our render buffer descriptor, our initial one, so we could say to the camera color buffer, hey, bind the multi-samples rather than resolving them as you're processing. So we needed access to the scriptable renderer to be able to do that. But it turns out storing 4 times multi-sample anti-aliasing texture requires 4 times the external memory space. So that has a lot of performance overheads. We also found that in order to do this, it required Vulkan support for Oculus, but we were stuck in OpenGL just given the position of our project at that time. So this was not a solution either. The solution that we ended up finding that worked for us was to use fast approximate anti-aliasing, which selectively smooths out high contrast pixels via edge detection. And it's essentially multi-sampling around a pixel to filter for high contrast and then performing a blend operation on that. But the great thing about fast approximate anti-aliasing is it can be combined into our final blend. It doesn't need another pass prior to doing the blending. We found that Unity's approach was decent but produced artifacts. And the current standard for FXAA 3.11 uses additional multi-sampling, and just like Blur, the more multi-sampling you have, the more expensive it can be. So we needed to kind of find our own custom solution to this, and we'll start to talk about that next. I just want to show you an example of the artifacts that Unity's FXAA were introducing. So in each of the corners of our high contrast derivatives, changes in color there, we start to see all these artifacts being added as it's trying to find the best way to blend between those colours. And this was very undesired, and we really didn't like it, so we had to find another way around it. So now with FXAA applied, our scriptable renderer looks like this. So in our post-processing pass, we're doing our bloom filter and our downscaling and upscaling, and then within our final blit operation, our final blit pass, we're then doing our FXAA on the camera color texture. Then we're taking our bloom texture and adding to that, and then we're outputting to the display. And so this is pretty fast and pretty helpful. But as I was saying, we've still got some artifacts occurring, and there's certainly more ways that we can optimize it. So we'll go through them now. So as I was saying before, neighborhood sampling with any kind of anti-aliasing approach, especially when you're dealing with a full resolution buffer like your final camera color. When you're starting to do 5 or 9 fetches, it can be really expensive. And that final blit where we were just using, I think it was Unity's FXAA, was costing about 1.5 milliseconds, which was pretty pricey. So we needed a solution to be able to reduce that multi-sampling, so we weren't sampling as many pixels from our buffer. But really, we didn't need to sample the whole screen. We didn't need to smooth out every pixel on the screen. We were already using MSAA, and that was doing the bulk of the work for us. We really only needed to smooth out our HDR pixels where the issue was occurring. So maybe that filter we used earlier could be handy. So in this example, in this image, anything that's yellow, we know that's a HDR color. So we only need to work out where the edging, the high contrast pixels are with our mask in mind, in order to do the smoothing around them. So by taking this approach, we could essentially filter out any colors that weren't a HDR value. Then we could sample the neighborhood around the remaining pixels. Then we could apply our contrast filter, and then we could blend our pixels. So the final cost of this was about 1.2 milliseconds for these images. But the problem there was that we then reintroduced was we had actually made our smoothing less effective, and that was because now that if we take an edge here where this side's white and this side's black, this side has the HDR pixel value. Well, we're only sampling on this side. We're no longer sampling on the side that gets discarded, so we can't effectively find a nice blend between the two. We can only blend on one side. So we reintroduced aliasing by trying to optimize. So that was no good. So we were finding that still actually our performance was not optimal when the screen was flooded. In addition to having our aliasing back, even though we'd approved the final blit, we still didn't have enough optimization. So we still needed to work out a way to reduce sampling and reduce the amount of times we're reading from our external memory. So we did realize that we were performing the same masking operation twice. So could we use our bloom pre-filter, the filter that goes through and determines what pixels are going to be sent down through the downsample blurring effect? Could we take that bloom pre-filter and output that as a mask for our FXAA to read in, so that we didn't have to do the mask operation again when we were sampling our FXAA? And turns out, yeah, we could do this. So when we take our camera color in for our bloom filter, it's going to, we can essentially take, once we do our bloom filter pass, we can take out a saturated or illuminant saturated version of that and store that as a mask in the alpha channel. And then we can take the RGB from that blue filter and still send that down through the horizontal blurs and the vertical downscale blurs. And then as we go back up again, we're blooming and blooming, we're blending the horizontal and the vertical blooms back together again until we get to our final blend, where we can then add our mask back in so that our final bloom blend now has color in it as well as the mask back in its alpha channel, and that gets sent out as a texture into our final blit as it normally would. But rather than just reading the RGB instructions, we're now also going to read the alpha data. Hope I explained that fairly well for you guys, because it was a bit for me to wrap my head around when I was trying to write it. And then so we send that alpha channel, we take that alpha channel and we basically send it as a mask into our fast approximate anti-aliasing operations and discard any pixels that are outside that mask prior to doing any further sampling in the FXAA path to find the rest of the neighbourhood. So if we just have a look at a bit of that, have a bit of a look at that from the code side, as we come into our fragment pass for our filter, when we sample our screen texture and then we do our filter function on it, and then if there's no colour in that filter, then we discard the pixel, and then we take that mask that we've generated and store that in the alpha channel. Then we do all our downscaling and upscaling, and in our final upscaling pass, we read in that alpha mask again, because the bloom filter render buffer is the same as your last high mip, and that'll get blended together. And so then we get the RGB blended data, and we also have our mask back in our final upscaling blit, and then we blit that out as a texture, and then we read that in as a bloom texture in our final blit pass, and we can take the alpha value from that and pass it into our FXAA, and then discard the pixel there again, because it's the pixels that Shooty rejects that make Shooty Skies the best. Sorry, I couldn't help myself there. So this had another issue where we had to relook at how we were formatting our bloom render buffers. Essentially, the graphics format for the HDR buffers that Unity seems to support for Unity seems to support for Android doesn't have an alpha channel. I couldn't find a supported HDR buffer format with an alpha channel. In that giant list of graphic formats, textures, there's no real discernible way to find out which ones are actually supported for your platform. If anybody has a way to do that, please let me know, because trial and erroring through that was ridiculously hard and pointless. So in the end, we went to change it to a standard R8, B8, G8, A8, S-float format for the buffer. And because of this, we're going to lose some precision and lose some color, but we're also going to gain a little bit of performance back. So it's kind of, a win-loss, but we could account for that loss of precision, loss of color by adding some tone map and color grading back into it. So when we do our bloom filter, we tone map the color, so we're trying to preserve as much of the color data as we have prior to cutting it off and sending it down to a SDR format. And then when we're doing our upscaling again, when we're blending the high maps and the low maps together, we're doing a saturation and a vibrance pass, just to try to replicate some of the color that we'd lost. And so on the left here, the emission is a bit blown out and a bit too white hot for my liking. So the saturation, the vibrance, color grading really helped to get some of that color back and suit the feel of the world that we wanted. Another happy benefit of pushing the mask through the bloom, pushing the mask out from the bloom filter, is the natural bilinear filtering that was happening with the downscaling. So as we take our camera color for our bloom filter, to perform a bloom filter, the first thing you do when you set up your bloom filter in its descriptor is downscale it. So you're performing all your bloom functions starting at a half-res texture and halves from there on. But you're halving with a bilinear filter, so that's already starting to make the mask a bit more blurrier. And then we also did another little quick blur pass in the bloom filter to help reduce flickering, as well as add a bit more fuzziness and blur to that mask that we're going to get out. So if you have a look at these images on the right here, you can see what the mask would look like without, as it comes out. As it's being downscaled and then upscaled again, we get all this additional fuzziness around the edges. And even though there's a bit of aliasing there, that fuzziness is now actually allowing us to sample both sides of the edge again, because that fuzziness is sort of bleeding out from the hard edge of the HDR pixels. And so then we can sample both sides of the edge again and get a nice blended, nice contrast filter working and a nice blend occurring. So this is like a final example of what the blend looks like. So we have, with FXAA off, the HDR colors are still staircasing and really jaggedy, but once we have a HDR masked FXAA filter on, we got a really nice blend going on, and this made it visibly tolerable and made the experience far better. Another quick thing worth mentioning that we were able to do with the Scriptable renderer was have better memory management. So we were able to set each render buffer, we were able to set its load and store operations within the custom Scriptable renderer. And this allows us to have better management over our external read and write bandwidth transfers. So as we were saying, when we look back at the Quest 2 hardware, each time we're reading and writing from the external memory to the tile memory, that's really slow, and we want to minimize that as much as possible. So if you take a look at our game, for example, when it comes to doing the camera buffer operations like reading and capturing all our opaques and transparency and then the color, the post-processing paths, we don't need to load our previous frames data, and we don't need to store it again. It's unnecessary. We clear our camera every time to our skybox, so we can basically say, hey, don't store the color and don't store the depth, and that reduces the amount of times that we're writing and reading and writing from external memory. And the same thing, we can do the same thing with our bloom buffers. Because they're getting rendered with the final bit in a single render pass, we don't actually need to store any of the data on our bloom buffers, so we can tell Unity not to care about it at all. So in the code over here, for basically every blit that we do, we just basically set our render buffer actions to don't care, don't care, don't care, because we don't need to store that color and we don't need to read from that color in pretty much any instance. Unity by default will store color just due to the modular nature of the render passes and how they work. They can't guarantee that at some point, if you don't store the color, you'll receive, you won't be able to read from it again. And the way you configure your Unity application, it may want to try to read from it again, and then you'll end up with a black screen. So being able to be more explicit here, we were able to get some more memory management, a bit more performance back that way as well. So for final benchmarking, Unity's forward renderer with its post-processing stack attached for Bloom. Their Bloom cost about 2.5 milliseconds. Their final blit was about 2.3 milliseconds, and that was another render pass in this example for a total render time of 20.5 milliseconds. So in that instance there, where we've got the additional render pass happening underneath, it's doing that store and read write. It's using its store and load operations again, so we're accessing external memory more than we'd want to be. Whereas with our own renderer, our Bloom's running at 1.3 milliseconds, our final bit's at 2 milliseconds, and our total frame render time is about 18.5 milliseconds for when I was doing this capture. And that's running at 72 frames per second, which is great. So now we have Bloom, color grading, on top of our standard render pipeline, and the game looks far better for it. So just in summary, we were very ambitious with what we wanted to achieve with Shooty Skies graphics update, but I think we were pretty successful in the end. Scriptable render features are great for plug-in and play tools, but lack optimization. Scriptable renderers beyond that allow you to get your hands dirty in the nitty-gritty and be far more explicit in your design and approach. The Quest 2 really doesn't support what we wanted, but we designed our pipeline as best we could to suit its architecture. Bloom is very expensive in how it's being rendered, and really should be designed into your program early on so that you can manage its constraints from the ground up. And there might be better solutions than what we did with FXAA, but that worked well for us and it ran at the frame rate we wanted, so we're very happy with those outcomes. And just a reminder, I'm not a graphics programmer, so I hope I was able to explain everything to you fairly well. Thank you. Here's some in-game footage captured with Oculus's terrible video capture, but it's the best way I could do it at the moment. And happy to take any questions if there's any time remaining, which there really isn't, sorry. So hopefully we can find a way to have a chat somewhere else if anybody has any questions. Thank you.